Okay, good morning from Serbia. Our first speaker of the day is Peter Morgan, a longtime friend of the conference, and he'll be talking about artificial general intelligence. Uh, Artificial general intelligence is the primary research goal and focus of many AI researchers and is a common topic in science fiction and future studies. Peter Morgan is the published O'Reilly author and will lead us through the vast meat. He will talk about what AGI is and what might be the myth and what does it really mean and how far are we from achieving something like artificial general intelligence.
Hey, I'm Peter Morgan. I'm going to talk to you today about the myth and truth behind artificial general intelligence. I am the CEO and founder of Deep Learning Partnership. We are an AI consulting company based in London. So here is an outline of the talk. So what is intelligence? General and versus narrow, biological versus non-biological systems. And then we'll look at artificial general intelligence, or AGI, and we'll look at what it would take to build such a system, and then we will conclude the talk. So basically it's a talk about AGI. And so why do we want to build AGI at all? Well, we want to solve general intelligence, and then we want to use that to solve everything else, right? So that's medicine, cancer, brain disease like Alzheimer's, Parkinson's. We want to live forever, longevity. We want to solve physics, maths, biology, chemistry problems, material science, and social problems we want to solve. Basically, we want to build a system that will help us to solve all these problems that we're busy solving anyway, and sometimes creating. But basically, if we could build a system that's as generally intelligent as us, and even more so, even more intelligence, ultimately super intelligent systems, then we could accelerate basically the progress that we're making in all of these areas. Okay, so what is not general intelligence? Well, we've seen a lot of very impressive displays of what we call narrow AI. We think about AlphaGo, AlphaStar, the company DeepMind here in London, and Deep Blue, IBM beating chess, and again IBM Watson winning at Jeopardy. So these are all super impressive examples, aren't they, of intelligence, because they're sort of superhuman levels at these very narrow tasks, like playing a board game like chess or Go, winning at a video game, which is a $100 billion plus industry these days, and solving linguistic problems. And so these are all these all are examples of narrow AI, but they're not general AI systems. So these again are examples of narrow AI. So what is general intelligence? How is it different from those systems? What are we missing? Well, Howard Gardner at Harvard in the 80s came up with this really good way of classifying the different types of intelligence. And he came up with about 9, possibly 10 different categories. We've got, mathematical IQ, which is the ones we looked at there, language. But then we've also got these other things that are very unique to humans, like interpersonal intelligence, how we communicate with each other, how we know what each other's thinking, theories of mind, that type of thing. And then we've got intrapersonal, where we sort of introspect. We can sort of examine our own thought processes. Computers cannot do that today, as far as we know. So these are uniquely human kind of intelligence levels. So we're certainly nowhere near getting towards those types of intelligence. So there's other ones there, maybe spiritual intelligence. We've got athletics. So building robots, intelligent systems that can navigate around in space. That's another type of intelligence. A little clunky right now, but we are making progress with that type of intelligence. So how far have we come? Can we put numbers on these things? Well, I've sort of come up, put my finger in the air a little bit, come up with some numbers. I think, the logical mathematical intelligence, maybe we've come 50% of the way. Like we saw, we can beat these narrow AI tasks quite comprehensively now, but they cannot do other things. We haven't completely solved language, for example. I put 50% on that. Musical, they can actually create music, art, these generative AI systems. So we have made a lot of progress actually in the last year, especially in the last decade, I think, with these artificial neural networks. But we still have a long, long way to go for the rest of the types of intelligence, robotics, interpersonal, intrapersonal, understanding of nature, our surroundings, what's good, what's bad, sort of moral intelligence, ethics. Yeah, so subjective intelligence, conceptual intelligence, we have a ways to go there. And existential, our place in the universe, I don't think computers can think like that just yet. Basically, they're statistical systems. So how will we build AGI? Well, it takes a village to create a child, and I think it will take a village to, or at least a team of scientists from different backgrounds to create an AGI. So that will include computer scientists, physicists, neuroscientists, psychologists, the usual suspect, I think. If you think about the human brain and what we do, humans do, we're going to need all of that expertise from all of those areas. Okay, so let's have a quick look at the difference between biological and non-biological intelligence. We'll drill down a little bit there. And so with biological, we've got plants, bacteria, insects, and mammals, including us. So we've got a range of intelligent systems. Plants have their own intelligence. They're able to survive in their environment. They can't do some of the things that we can do, but they still manage to survive. That's a type of intelligence. Moving on up to bacteria, which can move around and do a little more than plants. Insects, of course, like say the bumblebee, quite intelligent. They can communicate with each other when they find something, some pollen somewhere, and they know how to navigate all of that. And then we've got mammalian brains, say, for example, monkeys, very clever. They have their communities, they live in community, but they can't sort of conceptualize to understand the universe. They can't do math. They do have language. Most animals have language, in fact, birds. Think of bird song, etc. Even insects communicate with language, a very primitive type of language. But we are the only mammal that can actually conceptualize our environment. We have a sophisticated language. We can do mathematics and physics and all that good stuff. And, I guess our consciousness is at a slightly higher level, perhaps, than all the other mammals as well. And consciousness, of course, is a part of general intelligence. And then we have the non-biological. This is how we're going to try to make AGI. It's artificial general intelligence. So that include digital processors, CPU, GPU, FPGAs, and ASICs. Neuromorphic, which is a more analog-based, bio-inspired, based on how the brain works. And then type of hardware. And then finally, sort of question mark, do we think quantum computing is needed, or will it give a different type of intelligence? We'll very briefly look at all of these things. Okay, so there's some of the examples in biology that we've talked about. Biological systems are hierarchical. They go from sort of atomic molecular level right up to the body, the system. So, we have atoms, cells, neurons, systems of neurons, and then our whole central nervous system. And then if we look at these neurons, they are very complicated systems, in fact. So, intelligence is very unique, and I think we do appreciate, we don't sort of understand consciousness or how it would even arise, for example. So we do understand, there's something a little bit unique about especially human intelligence and consciousness. So maybe it's no surprise that these individual elements, there's about 100 billion in the human brain, called neurons, slightly complex systems in themselves. And then you can see when we put, tens or hundreds or thousands of them together, and then millions and then billions, then we're going to get a very complex system out of which could emerge and does in fact emerge intelligence and consciousness, subjective experience, and all of those good things. So how on earth are we going to try to build something that complex? And then this is the brain. This is the sort of level where general intelligence does occur. It doesn't occur at the neuronal level. I don't think individual neurons are intelligent, but they're part of the system where you put 100 billion together of different varieties of neurons, of course, and connect them all up in the connectome, whether that's humans or primates or even insects. The sort of intelligence occurs at the full system level. And then, the last bit of the hierarchy is the central nervous system in all animals and insects. So, the brain is attached to the body, right down to our toes. Some of the neurons are 6 feet long, etc. Very long systems here are very complex. Biology's had, 12 billion years to evolve, and this is where we are today. Very complex systems, quite amazing and unique systems, in fact. And then if you wanted to go one level higher, then you could start thinking about communities. We do act in communities, cities, countries, and internationally. Okay, so that's sort of biological that's biological intelligence. Let's look at non-biological hardware and how we might build intelligence from that. Okay, so we've got different types of processors: CPU, GPUs, ASICs. I put IPU on the end there. It's an intelligent processing unit from GraphCore. It's basically an ASIC designed specifically to optimize artificial neural networks. The GPUs are very good at it, but they have their limitations. CPUs can do it, but they're the least efficient system of all to run an ANN on. Or a deep learning artificial neural network, whereas GPUs are slightly more efficient, and then the ASICs, of which the IPU is just one type. There are many, many companies these days, dozens of them, set up primarily in the last 10 years to build systems optimized for artificial neural networks. So interesting time, in fact, in this whole process of humanity trying to build an artificially general intelligence system. Okay, so those are all silicon-based systems and digital. And so these are the artificial neural network I spoke about that will be running on these things. Different architectures for different purposes, say computer vision, language, be slightly different architectures. And so just kind of looking back at our history and seeing, where we came from in the 50s, in the 30s, we had valves, and then we went on to transistors in the 50s, and so integrated circuits. And I mean, this is 1970s. We had the Cray 1 at 160 megaflops, pretty impressive at the time. But then, today, right up to date, 2020, 2022, we've got the CPU there. We've got a GPU, NVIDIA, Intel CPU, NVIDIA GPU in the upper right-hand corner there. And then we've got a couple of ASICs. We've got the Google TPU, and we've got the GraphCore IPU. So this is kind of state-of-the-art today, as opposed to the Cray that we saw in the previous slide. Okay, so there's a whole rack of Google TPUs, basically, and that's over 10 exaflops. And so that means that it's about 100 billion Crays that we saw earlier. 100 billion fold increase in hardware since 1976, roughly 50 years or so. Very, very impressive. We are, however, reaching the limit of physics in terms of Moore's laws ending, the exponential doubling, or the doubling in the number of processors we can fit on a chip. Transistors on a chip every 2 years, doubling. So we're kind of running out. We're down the laws of physics. After you get down to about 2 nanometers, you get quantum tunneling, and the transistors break, basically. So we're kind of, the Moore's law is kind of flattening out a little bit, but we've made so much progress. The question is, though, will I be able to create, or will we be able to create general intelligence from a rack with 10 exaflops? It's a very good question. So keep that in mind as we go through. Here's another system. That's the IBM Summit. They've built even more powerful systems since then, and other countries as well. For example, China. And so these things again are multiples of exaflops, huge memories. So again, the question we need to ask: do you think general intelligence will sort of come out of this digital hardware? It's a very, very good question to ask. Okay, so I guess now's the time to answer it. The answer is no. So what are we missing? The brain, right? It weighs about 1.5 kilograms, about 30 watt of energy. Those systems we saw use like 1 million or 10 million watts. Huge difference, right? We're talking, orders of magnitude, 10 to the 6 orders of magnitude. Okay, so the biology is clearly optimized for intelligence over the billions of years that we have not been able to do with our digital technology, no matter how impressive it is, pushing the laws of physics here. But yeah, it's a different type of structure and architecture. I think that's needed to build AGI. Okay, so clearly, sheer digital horsepower is not going to get us to generally intelligent systems, or we'd have them by now. So we've got 10 exaflops, right? And so we know that the brain biology uses a different architecture. Memory and compute are actually combined. So a neuron is not only a processor, but a memory as well. We call that memristors, memory plus transistors, both taking place at the same location in space. So perhaps we should be looking at the brain for inspiration if we want to really build an AGI system. It seems obvious now, right? But so why haven't we sort of been doing this? We'll hopefully answer that question by the end of the talk. So here we'll introduce neuromorphic computing. It's biologically inspired. First proposed, or most famously proposed, maybe by Carver Mead at Caltech in the 80s, but other people were working around similar ideas around the same time, as normally happens. And they use analog signals, so spiking neural networks, not digital, just so definitely bio-inspired. We understood how the brain worked by then. We had been dissecting and looking through microscopes and had a pretty good idea what a neuron was and how the electrical current moved through as analog waveforms integrate and then fire. When a threshold is crossed of information, then one neuron would basically fire across to the next neuron via the synapse connection. And so we kind of had a general idea how biological brains worked, whether mouse or mammalian, primate, or even human, because we'd cut them open. So how on earth are we going to build that in, artificial materials? Okay, so that's all we have to do, right? We know kind of, how intelligence works because, we work. So, but how are we going to build us basically using processors? That's the question. Okay, so right now we have built systems, the Spinnaker and the Human Brain Project and Brain Scales in the Human Brain Project. IBM have True North and Intel have a processor called Loihi. And there are also many startups actually these days. There's a couple there, but there's many. If you just Google neuromorphic processor startup companies, you'll find some more. And so we have up to 1 million cores, maybe 1 billion neurons, which is about the size of a mouse brain, okay? It's 100 times smaller than the human brain. They can do mouse-like tasks. They can navigate through space, for example. But mice can't do much in terms of conceptualizing, certainly don't do math or anything. They have a very basic language. But so we've kind of built mouse intelligence in a way. Not quite the same, though, not conscious like a mouse would be conscious and have subjective experience, feel pain, for example. These processors don't, as far as we know, feel pain. And so we basically need to scale that up 100 times plus add a little bit more. So this is sort of where we are. We're probably at 1% of the journey, but often these things can be exponential, like the Human Genome Project, for example, is in the normal silicon digital processor. These are all on exponential curves, so doubling every couple of years may not take us 200 years to get there. It may take us 20. Okay, with the exponential on our side. Okay, so and they do use a lot less power than digital. So instead of 1,000,000 watts, we can do it at about around 1,000 watts, for example. And so Spinnaker has been available on the cloud for 5 years. You can log in today, set up an account if you wanted to. Okay, so there is an example of Spinnaker, the neuromorphic computer. They're slightly bigger now. I think they're on the Mark II version, probably twice as the size, and it's at housed up in Manchester, where the Professor Ferber, who's leading the project, is based. He was one of the co-founders of ARM, by the way. Okay, so very, very exciting stuff. There's an example of an analog neuromorphic computer on the left, the brain scales, and the Spinnaker was actually a digital neuromorphic, so there's slightly different architectures there. The brain, again, I said a spiky neural network, so it's kind of a combination of digital and analog. The signals are analog, but the fact that they sort of have to reach a threshold before they cross the synapse to the next neuron is a kind of a digital thing. So, there's no it's purely analog or purely digital. It's sort of a combination of both. The brain, the biology is. So these things are sort of a slight mix of analog and digital. So we've got brain scales on the left, analog, and we've got the definitely digital Google TPU ASICs on the right, just for comparison's sake. Roughly the same size, but one will give us a sort of general intelligence task, but in the other will be able to do super good at math. But they're not going to do other stuff that the biological brain can do or the neuromorphic hardware can do, even though they're roughly the same size. By the way, the one on the left uses about 1,000 times less energy than the one on the right as well. Okay, what about quantum? Very quickly with quantum, so basically the brain is warm, it's wet. So most people think probably there won't be quantum effects involved in a AGI, but obviously as scientists, people are open to, at the very small scales, perhaps there's something quantum going on. So we probably won't be looking for the quantum computer. We're probably focusing mostly on neuromorphic hardware, but I sort of threw this in for fun, really, a little bit of fun. Okay, just to say that, we're building quantum computers, but personally, I don't think we're going to need them for intelligence, general intelligence. Okay, so yeah, just to summarize everything we've spoken about, we have the 4 different types of processor: digital, neuromorphic, quantum, and biology. And there they are, and looking at the processors that we've, the quantum, neuromorphic, and digital processors we've built. Very, very clever progress has been made to the point where we can build these things, and then we've got the biological system there in the middle. Okay, so we've got 3 stacks, 3 non-biological stacks: digital, neuromorphic, and quantum. And the data center of the future will no doubt have all 3 types of compute hardware: digital, analog, and quantum. But we're focusing on AGI, so let's just see in the last few slides what that's going to look like in terms of building it. All right, so what do we need? What are the different approaches, and how are we going to build artificially general intelligence systems? Okay, so the thing is, the brain is a physical system, so we're basically going to need all of the physics that we've, as a species, developed so far, and then apply it to the brain. So neuroscience, basically, plus computer science, plus physics, plus psychology, as we saw at the beginning. So there are basically all of that we've understood about the universe, all the physical laws there. So we've done pretty well with understanding the physical laws. I don't think there's anything missing really for the brain. It's another physical system. So if we apply those laws to intelligence, then we may, with a lot of hard work, build a artificial general intelligence system. So intelligence is conceptual, objective and subjective. This is why we'll need the neuromorphic. I mean, right now the digital processes are purely objective, but what we as humans can do, what biology can do, is conceptual intelligence and subjective intelligence and experience, as well as objective. We can do the math and everything like that. In science, that's all objective, very nice, but we can come up with concepts of the universe, of each other. We can come up with theories of mind, and we feel stuff. You know, we feel pain, physical pain, we feel mental pain. We have all of these types of emotions. So digital hardware certainly won't do that, but analog and neuromorphic probably can. Okay. So can we build general intelligence? Well, we have candidate theories. We have good theoretical models of the brain. You can buy huge, thick textbooks and read thousands of papers with millions of equations, all describing how the brain works. So yes, we have theories. We have candidate theories of how the brain works. We have hardware. We have the neuromorphic in particular. We have algorithms and software. We've written frameworks for these neuromorphic processes, and we have a lot of good data sets these days as well to feed it data, whether that's written papers or data from the environment. We've got a lot of good data. So we need to build a complete software framework with libraries, software that will run on neuromorphic processes. We have to build the hardware, scale it up. We to 100 billion neurons. We're not quite there yet. Maybe in 10, 20 years we will be. It's like an Apollo project. If we really, put the manpower in, we have the Human Brain Project. But if we put the manpower in to developing these processes, then it will happen quicker. And we are actually putting billions of dollars. Here's some huge projects here. The Human Brain Project, $1 billion at least funding. The Brain Project in the US, Human Brain Project in the EU, Google Research, DeepMind, China. All of these are $1 billion+ projects. So, there's a lot of effort, time, resource being put in, money being put into building an AGI system. Well, that's doesn't make the news so much, but there is a lot of work in universities as well as big companies, government projects. Okay, should we build it? Well, there's safety and ethics to worry about, and we have the singularity where these things get as intelligent as us or more. Maybe a runaway intelligence. We have to think quite carefully about all of that. That's probably another discussion. Okay, so here's some AGI projects. I'll let you look at that in your own time. Running out of time a little bit. Just to know there's many projects in many countries, startups and big organizations. Okay, so how are we going to coexist with AGI? Well, there's lots of books and movies. Terminator being one of the more famous. Tons of sci-fi books. People love writing about it and making movies, especially scary ones. We've thought about this a lot, fiction and non-fiction. There's several takes on this. They will never be super intelligent, but that's unlikely. I don't think there's anything in the laws of physics that will stop that. We're intelligent, so why not? If we can build it bigger and faster, I don't see why we shouldn't be able to build super intelligent systems. They will be benevolent. Well, I hope so. Fingers crossed. We will merge with them. That's what Ray Kurzweil thinks. That will avoid this sort of problem of running away from us. Will be part of us. We will go to the next phase of evolution. It's all kind of sci-fi, but these are good things to think about in advance. They will destroy us. We don't really know, to be honest. I can't reassure you. It's my job. I'm not here to reassure or scare or do anything to anyone. It's up to each of us as individuals to make our own minds up and take the action that we want to. Either get involved building them, or help join an ethics society or committee, or just get involved. But I think everybody at the conference, we're mostly from a computing background, so we're sort of involved anyway. As it becomes more mainstream, I'm sure we'll all start programming these things or working on them in some way. There's some nice reading, The Road to General Intelligence. I think that's out just this year. Singularity is Near, Ray Kurzweil, and our final invention, James Barrett. All good reading. Okay, so conclusions. So it's obviously that obvious to most that deep learning or artificial neural networks running on digital hardware won't get us to AGI. It's based on statistics, not physics or biology, but how the brain really works. So it's an approximation. So we do need a complete theory of general intelligence. We need credible research turning to biology. Bioplausible models are appearing. The hardware is appearing. The software to run on it. And so will we have real AI systems in 20 years? I wouldn't doubt it. Sort of human level, maybe not super intelligence, but, getting to that point, 2040s, something like that. And we still have to wait for the hardware to mature and scale exponentially, but they're on a Moore's law. These neuromorphic processors will be the ones that get us there. Final takeaway, using basic physical principles, AGI systems will be built over the coming 20 years. Thank you for your attention.